Okay, so let me know if you have questions before we shift gears into a different topic, which is code pipelining. Are we good to start? Are you guys back?
Yep.
Yes, I'm here.
Okay. Back. Okay, good. So pipelining. So what we have done so far, if you remember our full stack stuff, right? We have been focusing on the architecture side, but we started from, in fact, it's like starting down top, like looking into the memory, both cache, hierarchy, and off-chip memory. And then I delayed the pipelining, which is the core itself, like the processing element, the processor, the CPU. This also applies to GPUs and others. I delayed it in purpose because I would like to discuss it first, and then we move from it into more advanced topics like out of order, superscalar, multi-core, multi-threading. So it's better to discuss both topics together because pipelining is the foundation for the other advanced topics. One thing before I start, I'm assuming that most of the undergrad universities are having at least some discussion of pipelining. If you are an undergrad of ECE, is this the first time that anyone hears about pipelining or how it works? Just to make sure what level of detail I should go to. Is there anyone that this is the first time that he knows even what is pipelining? Or you guys at least have some idea and you cover this to some extent in your undergrad? That's a question. No comment? So it seemed that I got disconnected, right?
Yep.
Okay, so what I was saying is I was asking if this is the first time that, is there anyone that this is the first time that he hears about or he or she hears about pipelining, or at least somehow this is covered in an undergrad to some extent. So this is the first time that anyone knows what is pipelining?
For me, yes, first time. But that's because I didn't take any of the computer architecture courses in
Good.
undergrad. So
Okay, thanks. What about others?
Brand new for me.
Okay,
Everything's
Jackson.
gonna
Okay.
be brand new for me.
Okay, thanks a lot. Thanks for saying that. So something to understand is, as I said, like the first part of the course is like the purpose of this first part is exactly that, is to make sure we are all on the same page. But on the same time, the topics we cover are usually covered in multiple undergrad lectures. So you might find that I go somehow in details, but in a quick way. So what I would suggest, especially for those who take these shots as new, two things. First of all, I'm going to post the recording specifically for that. So please make sure you go through the recordings, maybe more than one time if you wish, and feel free to ask questions, send me emails when you need to. The second thing is, for those that already know what are these concepts, going quickly through this, I usually find helpful even if you know the concept, because maybe I touch it in a different angle, I put things together, I explain it in a different way. Maybe you forgot because this was your second year, third year course. So it's helpful from both sides, those that hears it for the first time and those that knew it from before but need some refreshment. Good. Okay, so what we covered so far is what is the big picture of computer architecture, cyber physical systems, how they connect together, what this course is about. And then we said the first part of the course will be touching briefly about the basics of computer architecture. Again, as I said, we started by caching, then moving to main memory, and then now we will do pipelining, right? And after pipelining, we will touch on the advanced topics like multi-threading, multi-core, all the things you hear about in the media, maybe also GPUs to some extent. So let's see how far we can go. what we are going to do, we will start by saying what are the principles of core pipelining, why they are very beneficial, why they exist almost in all computing systems right now, but what are some of the challenges they face that can cause some problems. This will take us to what we call data hazards and control hazards that affect the performance of pipelining and how to identify them, how to identify their effect on pipelining, how to compute some performance metrics for pipeline, and compare different pipelines together. Again, some readings for those that, especially for those that see this topic for the first time. This is a book of Hennessy and Patterson, Computer Architecture, a Quantitative Approach. I highly recommend that you read these chapters. In fact, they are the appendix because it's considered review for the book, but they are very detailed as well. So they will be very beneficial and kind of supplementary material to this lecture. Good. So what is this complex figure here? So what we have here is what we can call a single cycle data bath, right? What is a data bath is what happens inside a very simple ALU processor. So assume I have something that is like an ALU here, which is an adder, subtractor, whatever. And then I have an instruction cache. This is our cache that we kept discussing in the previous 2 lectures. And then this is a program counter. What is a program counter? For example, you start executing your C code from the main, instruction by instruction. So you need to keep track of what instruction are you in right now and which instruction to bring first from the memory or fetch first from the memory. And the program counter is the one that is handling that. So it's a special register that stores the current address. It's in fact not the address of the current instruction, the address of the coming instruction. Good. And then this ALU usually takes data from a register file because it deals with registers. For example, if I do an add instruction that has R1, R2, R3, in your C code, this might end up something like if you have y equal x plus 3, something like this. This will be translated through assembly into an add instruction that adds 2 registers and then put the result in a 3rd register. Good. This will be added together. So an add requires some data to read, and this will come from the register file. Then go to the ALU, execute the add, store the results either in the memory or in the register file itself, right? So this is an instruction cache, and this is a data cache, because sometimes, as we said last lecture, L1 cache especially can be split into instruction and data. Good. So what is the main point we want to make here? The main point is that all of this, in fact, can be executed in a single cycle, which means you fetch the instruction, do the operation, store back the instruction result into the register file, all in a single cycle. It's called single cycle data path. So we don't have any notion of what I would say sequential logic here. Everything is combinational to some extent, right? Except that putting the data in the register file or accessing the data caches, which is like the input to your combinational logic and the output of your combinational logic. But all the combinational logic is done in a single cycle. That's good. That's very simple. That's perfect. But that's also problematic in modern processors, because now finishing everything in the same cycle, you would require a large cycle width, right? On the other hand, your period for the cycle would be large, which means your frequency, for those who are not in the field. So basically this is your clock. For example, you have a certain period. That's not an even clock, but anyway, this is your single cycle operation. This is T, which is called the clock period or cycle period. This determines your frequency of operation. For example, if you have a processor that is 2.4 gigahertz or 3 gigahertz, based on what you have, F is in fact the 1 over T. So how much you do within a single cycle will affect the frequency you are running at. So if you do everything in a single cycle, your T will be very large, which means your F will be very small. Good. You don't want your processor to operate in a 200 megahertz, for example. You want to operate in a very high frequency, which in turn means you need to reduce a lot T. But how can I reduce T while keeping exactly the same number of iterations, the same number of operations, or the same type of operations being done? Can someone give a hint on what I can do? Did anyone take Dr. Nicholas' course last semester?
Yes, I
Yes, most of you have done, right? So did you try to optimize the running frequency to some extent, or no?
Yes, there is like the pipeline is one of the idea to like break down the computational logic. If we have like a high, like a complex computational logic, we can break it down into multiple stages.
Perfect.
And we put register between this computational logic to
Correct.
increase or to increase the frequency.
Correct. That's exactly the idea. Is I want to do the same operations, but no one said you need to do them all in a single cycle. If you break down your logic into registers, you put registers in between different operations. That means now you reduce your cycle width, because instead of saying I want to do all these operations in a single cycle, I only do part of them, which means your T will become less, which means your F will become high, right? So pipelining main idea is you break down your steps into smaller steps, allowing you to run in a higher frequency, right? This is kind of a very brief introduction to someone who hears about pipelining for the first time. Good, but all what we said is usually referred to as pipelining, right? But that's the wrong terminology. What I said like 30 seconds ago wasn't in fact pipelining. It was just multi-cycle, right? Which means breaking down larger steps into smaller steps by putting registers. This is called multi-cycle, which means you take different cycles, or like number of cycles larger than one, to execute the same operation. But that's not yet pipelining. Can someone explain what remains to do pipelining?
So interleave the operations between.
Exactly, interleaving the operations, right? Because the idea is, okay, to explain in a high level, aside from this complex logic, assume this block of operations, the one that I want to execute. Previously, I was reading from the register file at the beginning, so that's a registered operation, and putting the register, the result back at the end. All of this is just a single cycle. This is what we call the single cycle data path. On the other hand, I am breaking this down to say I have exactly the same number of operations, but I'm breaking them down into steps. Those steps will be like the following: 1 step, 2 steps, let's say 3 steps for now. And between each step and the other one, I'm putting a register, because you need to keep track of what you have done to take the result back into the coming, to take the result forward into the coming stage, right? So here, this is a register, and then you still have the output register and the input register. So this is the previously very large block. By breaking this down into these registers, now you have 1 cycle, 2 cycle, 3 cycle operation instead of a single cycle. In fact, it's 4 because of the result, but previously you had 1. So now it's 4, right? But yet you didn't have any pipeline, because there is no overlap. You just, for example, you feed 1 input, execute 4 cycles, and then finish. But someone can ask, if I already have these registers now, once I finish the first stage of the first input, and I move to the second stage, this hardware now is not utilized. It's an empty, right? Which in fact I can use to input another input to operate. And once this is done, the other one here would be moved here. So this will be empty, so move it here. So you start overlapping your operations, right? So in a multi-cycle operation, you have something like that. Example we had is like 4 cycles, but you finish the input, the first input, before feeding the second one. But now with pipelining, you move this forward and say, I'm going to overlap operations before, because this cycle, once done and moved here, the hardware is empty, so I can use this one. So if this is your hardware 1, 2, 3, 4, this will be hardware 1, 2, 3, 4, and this hardware here is different than this one, so it's safe to overlap. Is the idea clear? Good. Okay. This is a bit of a detail, but might be good to go through. Assume, just to have a feeling of some of the numbers, right? Assume I have a single cycle processor And my clock period right now, T, is 50 nanoseconds. This is the period. And because I have a single cycle, so by default, you have CPI is cycle per instruction. It's a metric used in architecture, meaning how many cycles you take to perform a single instruction on average, right? So CPI is 1 because everything takes a single cycle here. Your performance simply is how many cycles you take per instruction is 1, and the single cycle is 50 nanoseconds, which means you take 50 nanoseconds for every instruction. Very simple, right? Let's see what multi-cycle can introduce to you. Assume I have a different operations. I have branches that take 3 cycles, loads stores that take 5 cycles, and ALU operations that take 4 cycles. And I have the distribution of these, right? Your program has 60% ALU, 20% load stores, and 20% branches. How this can be helpful? Assume because of pipelining, sorry, not pipelining, my bad. Because of multi-cycle, I was able to reduce the 50 nanoseconds into only 11 nanoseconds. Good. And from what you can see here is that in fact you take 5 cycles to induce the loads. So what would be my CPI, my average cycle per instruction? My average cycle by instruction for the ALU takes 4 cycles, and they are 60% of the operations. For the load, it's 50. For the load, yeah, it's 50 cycles, 20% of the operations. Branches, 3 cycles, 20% of the operation. This gives you a total of CPI of 4, which means on average you can finish 4 cycles. Sorry, a single instruction takes 4 cycles to finish. That's too bad, because here I only took a single cycle, but here I take 4 cycles. What does it mean? It's worse? Does it mean it's worse? No, right? It's not worse. Why? Because your cycle is different. Here your cycle is 11 nanoseconds, while here your cycle is 50. So if you calculate the actual time, not the cycles, 4 multiplied by 11 gives you 44 nanoseconds on average per instruction, while here your average is 50 nanoseconds per instruction. So now on average, an instruction finishes faster because of pipelining. Does this make sense? Are we good? Okay, so now this is all without introducing pipelining, without introducing the overlap, right? So as we said, if you do a multi-cycle operations, that first of all, single cycle is everything is a single cycle here. Once you are done with an instruction, you execute the second one. In a multi-cycle, you break down this into stages. Here there are 3 stages, but you still don't overlap. On pipelining, on the other hand, you overlap this, right? And you overlap this because you can utilize the hardware, which makes things much faster, right? Good. This is an example of how like you can pipeline your actual simple processor for 5 cycles. The first one, for example, you fetch your instruction. Your second one, you decode your instruction. We will see now what we mean by this. You do the ALU operation. You do a memory operation if you wish, and then you store the result back in a register. This is the very simple 5-stage pipeline processor, right? Good.
Doctor, can we go back to the previous slide?
This one?
No, the previous one.
Yeah.
No, yeah, this one. So I think in the multi-cycle one, we still have a pipeline, but at the request cycle, at the request bus, right? Or because we still have some sort, because if it's not pipeline, maybe the instruction fetch one should be like not overlapped. I mean, the instruction is a decode. It shouldn't come after the fetch. It should be first we get instruction 1 fetch done, and then the decode, right? So we have instruction 0 fetch, and then at the end we have instruction 1 the dot fetch. Is it like?
Oh, you mean here? No. No, right? Because, okay. That's in fact the overlap. So in a multi-cycle operation, this is a single instruction, right? The simple idea is that no 2 instructions exist in the system at the same time. At any point of time, you are executing only a single instruction. which is here instruction 0, and then after it finishes, it would be instruction 1. But what you are saying is that once I fetch instruction 0, I might start fetching instruction 1. This is exactly the overlap stuff, right?
Yeah. So this is two different instructions, right? I got confused
instruction
about
0
the
and instruction 1.
difference.
Yeah, that's two different
Okay.
instructions. That's correct. Yeah, that's correct.
Okay.
This is instruction 0 and this is instruction 1.
Okay.
Thanks. Okay, so the simple pipeline we are going to consider in our examples is this 5-stage pipeline. Fetch, which means go ahead and bring this is how your CPU in fact works in a simple way. First of all, once you, for example, run a program, Chrome or a C code or whatever, all the instructions get placed in memory. And then you access them one by one. How I access them? I go to the memory by the program counter, get the instruction itself through what we call a fetch operation, bring it to the registers, and then decode the instruction, which means try to understand whether it's an add, load, store, what are the registers, and then you execute the instruction itself, which means you perform the actual operation. Finally, you might need to store back the result in the memory stage, and or store it back in a register file in the write back operation. So a simple 5-stage pipeline is fetch, decode, execute, memory, write back. Good. Some examples and some kind of terminology that also architects use and we will use later is a scalar pipeline means in any stage you have a single instruction. For example, if you are fetching an instruction right now, you cannot fetch another instruction. Oh, is it possible to fetch 2 instructions at the same time? What do you think? Can we fetch multiple instructions at the same time?
I think yes.
How can we do that?
If we have multiple fetch units.
Exactly. If you replicate the hardware, for example, which in fact all of your machines, laptops, desktops are doing. We have what we call superscalar processors, as we will see later. How to do this is to replicate your hardware units. For example, for the fetch unit, you have 2 fetch units instead of 1, which means you can fetch 2 instructions at a cycle, not 1. Another terminology is in-order pipeline. What is in-order pipeline? In-order pipeline means if you have 2 instructions in your code, for example, you have an add, I don't know, add R1, R2, R3, and then subtract R3, R4, R5, or anything. Let's say there are no dependencies at all. This is R10. You have to execute your instructions, and in another sequence here, you have to execute your instructions in the order of their arrival. So you don't do any reordering, right? It's like first come, first serve that we discussed for the DRAM. On the other hand, you might, and in fact, all of our machines are doing this, you might need to reorder some of the instructions ahead of each other to increase throughput, right? This will introduce complexity, but it will hugely improve performance, as we will see later. This is called out-of-order pipeline. Good. The other terminology we have is what we call pipeline depth, which means how many stages you have in a pipeline. For example, the previous example we had was a 5-stage pipeline. And I guess also the previous slide was saying in a Pentium 4 was one of, I don't know if some of you already had the chance to own a Pentium 4, but I had a Pentium 4, I mean, like 10, 15 years back. And the Pentium 4 is 22 stages. i7 would be something that's very similar. Like most of the cores you have in your machines would be somehow between, I don't know, 15 to 30 stages, right? So it's a very deep pipeline. Good. This is called the pipeline depth. How many stages you have in your pipeline. Good. Let's see an example of how things execute in an actual machine. Assume I have 3 instructions. This is the first instruction I have, which means add R1 and R2. This $sign means a register. And then you put it in R3. So it's like R3 equal R1 plus R2. I want to execute this, so I start by fetching it, which is the is this yellow? This is the orange color here. Good. And then in the next stage, I move the add after I fetched it to the decode unit. and I can bring or fetch another instruction. Let's say our second instruction is a load operation, so I bring it here. Third, the add will move to the ALU, the load will move to the decode, and I have another instruction which is store that comes to the fetch. Good. And then moving forward, the add moves another stage, load goes to the actual ALU, and then store will move to the fetch. Finally, add will write back the result, load will go to the memory operation, and store will do the ALU. I'm done with the add, load is now at the final stage, and store is at the memory. I'm done with the load, and then I'm doing the store, right? So this is what we call a pipeline diagram, and very, very important to understand this, right? In this pipeline diagram, I have fetch, decode, execute, memory, write back. These are the symbols we have here. Each instruction takes 5 stages, and they are executed back to back, which means the overlap. Once you finish the fetching of an instruction, you can fetch another one. If there is a question here, let me know, please.
I have a question, actually.
Go ahead.
This would be regarding the structure of the pipeline. So if you want to keep a certain order in place, how would you ensure that this order always executes in order and not out of order?
Correct. That's an excellent point. You do this by here at the fetch stage, you have what we call a buffer where the instructions comes from the memory goes into this buffer, right? When reading instructions, if you do them in order, you have a first come first serve scheduler here that is not allowed to reorder stuff. So it takes it one by one. And once you fetch them in order, because things move in a line, then they cannot go out of order or they cannot mess up during the pipeline, right? Nothing gets ahead. Like if an instruction stops in a stage, the one after it will stop in the previous stage. And we will see this right now. Once you stall here, we will see now what we mean by stall. But if an instruction is waiting for something to happen, all the subsequent instructions will be waiting on the row. It's like, for example, you're going to the bank, you have a row. If the client in front of you is taking an hour, which is like too bad, no one will ask you to, okay, please come forward, I can help you. If there is no other agent, right? It's a single agent. So things are getting in order. If a client stalls, everyone afterwards will stall. Good?
Okay. No, I also wanted to understand in terms of implementation.
Yeah. So yeah. That's an excellent question, because, and also this is a good question when we come to out of order, because we will see instead of this first come first serve, we will do what we call out of order or reorder buffer, right? This is the logic that will be doing the reordering for us for in case of out of order. So good. Thanks. Is there any other question? Okay. Okay, good. So we have covered the single instruction performance, multi-cycle instruction performance. Let's look into the 5-stage pipeline performance. It's exactly our previous example where we had 50 nanoseconds per instruction for the single cycle. And if I remember correctly, it was 44 nanoseconds per instruction for the multi-cycle. What about the 5-stage pipeline? Assume now my clock period moves in the multi-cycle, it was 11, right? Now I make it 12, and we will come into why I increase it now, right? But assume my clock period is 12. If I finish, if you go back to this figure, if you are standing here and looking into what comes out of this machine, you see an instruction per cycle, right? Which means on average, you finish 1 instruction per cycle, correct? So that means you have, as if you have a CPI of 1, because as if each instruction is taking a single cycle, right? And then now, if your clock period is 12, you have an average of 12 nanoseconds per instruction, which means sitting here, you get out 1 instruction every 12 nanoseconds, right? This is for sure a huge improvement over the 44 for the multi-cycle. And this is the advantage of the overlap. Does this make sense? Good. So now comes the question is why, in fact, we had the clock period to be 12, not 11 as before. Because once you start introducing pipelining, you might have overheads. For example, to ensure the in-order example that I was giving to John, to ensure here you don't have any dependencies, no hazards, the things we will discuss later. So some of the overheads here will increase your clock period a bit. Good, but overall you get an improvement. Is that correct? So getting a CPI of 1, that's also a kind of an ideal assumption, because if you said here, okay, now in this example, yes, you get one instruction every cycle. But if you start having some stalls for some reason, as we will see right now, things will get delayed a bit. So you don't get, ideally there is no one cycle. Ideally it's one instruction per cycle, but generally that's not the case. In a practical case, you might have some stalls, right? And those stalls will increase your CPI. So a practical number for the 5-stage pipeline is maybe you have a CPI by 1.5, which means each instruction on average takes 1.5 cycles, or you get a performance of 18 nanoseconds per instruction, which is still much better than the multi-cycle one. Good. Is there a question? Okay. We already discussed this. You have latches and delays, pipeline hazards, extra data path, bypassing logic. So you have so many things that can increase the clock period. Because ideally, if you don't have any overhead, you would say, okay, the delay through the data path, for example, if it's, I don't know, 50, you divide by the number of stages you have, which is 5, you get a clock period of 10 nanoseconds. That's the ideal scenario. But because of the all extra overheads you have, like the register latching, the glitches, the bypassing logic, the wires, you need to increase this a bit. Why we are discussing this? Because that's one of the limitations why people don't do, for example, if pipelining is that good and it shows you a huge performance benefit, why I don't have 100-stage pipeline, 200-stage pipeline? And then instead of getting one instruction every, I don't know, like 10 nanoseconds, I get an instruction every 1 nanosecond. That's not possible, because once you keep increasing in the number of pipelines, this overhead will scale with you and it will start being the limitation, right? That's one factor why having deep pipelines is not the norm right now in our machines. I mean, by deep, something above like 30, for example, stages per pipeline. Good? Okay. We already also discussed this. And we will come into, okay, we said that we have many delays, we have stalls. That means CPI is in fact usually larger than 1 because of these stalls. Now let's see why these stalls happen, right? And again, let's talk in terminology. So we have what we call a dependency. Dependency means you have 2 instructions that depend on each other. Can someone give me an example of how 2 instructions can depend on each other?
Okay, we can, for example, like a data dependency, like for example, I will add 2 registers, and the sum of these 2 registers, I will use it in another instruction, for example. So this may be one of the dependencies.
Which means you need to wait for the result of the first instruction before executing the second one, right?
Yes, exactly.
So if you are overlapping these 2, you cannot continue with overlap because one of them is dependent on the other. So you need to wait until the first one finishes, right? And this introduces delays to the pipeline. This one possible thing. Also another control dependency, if you think in high-level languages, you have if conditions, for example, which get translated into jumps and branches in your assembly. You need to wait for your condition calculation in the if before determining which statement to execute. Are you taking the if path or are you taking the else path? This is called control dependency. And this also introduces delays, right? Good. What is a hazard? Hazard is, it's simply a dependency, so you have to have a dependency. But if you ignore the dependency, you will get the wrong results. This is called usually hazards. And we have 3 types of hazards: data hazards, control hazard, and what else? Can someone remember? Structure hazards, right? Like, and this we didn't discuss yet, but if you are trying to write to the memory, for example, there are no dependency at all. So Mohammed gave the example of add R1, for example, R2, R3, then subtract R4, but I need R1 here and R5. This sub cannot execute until the add finishes because it needs the result of of the add, right? This is called data dependency. But what if both instructions, they are not dependent on each other, but they write in a memory location? This brackets means a memory location, something like this. And then you have a sub. You also write to R1 memory location here, and you add other different registers. Here, the sub does not depend at all on the add, correct? It has its own inputs, R4, R5. It can perform the add operation, but then it needs to store the result of the add into the memory. The problem is that now you need to write to the memory location that is exactly going to be written by the add. So if, for instance, the sub goes to the memory before the add, the writes will happen out of order, which may cause some problems. If two instructions are trying to access a certain resource, this resource can be memory, as we will see right now, this resource also can be register file, or it can be even control path or flags. All of this is called structure hazard because two instructions are trying to access a shared resource at the same time. Good? Okay, an example of data dependency. These two instructions are completely independent because they don't have any common operands. But what about this one? This is very similar to the example we just gave. Here, the add is writing into R3, while the second add needs the result of the R3 to perform the actual addition operation, which means they have dependency together. What about the third one that we have? Can someone go through what other dependencies we have in the third example here? What do you think? Any idea? Hello? Oh, am I disconnected?
No,
I'm
Doctor.
still here. Okay, you are thinking or what?
So what is LW mean?
Oh, it's a load. Okay, so add, load word, add I, which means an add operation immediate as well. Sorry, I forgot. Maybe some of you doesn't know that the assembly terminology, but this is an add instruction, a load instruction, an add instruction, and a store instruction.
Okay, so the first one we add two argument and put it in variable 3.
Correct.
And then we load it, load again 3 and 4. What is 8 mean? The 8 number?
Yeah, so for the load operation, what happens is that a load is a memory operation, right? So you need a memory operand, which is an address. So this is saying, take the value in R3 register, add into it 8, which is an immediate value, go to the memory with this address, and then load the data in this address into register R4. This is what a load mean here. Okay, it's good to touch in assembly a little bit. I was assuming that maybe this is clear, but I'm wrong. Okay, so what about store? Store means write into the memory, right? So what you would do here, this is usually called offset. So you take the address in R7, add 8 into it, and then you need to write into the memory right now. So you take the value in R3, write it into this address. So this is a memory read because it's a load, and this is a memory write because it's store.
Okay. So for the second instruction, we cannot access the location, the memory address before the addition, the first instruction finish, because we
Correct.
need
Because you need the
S3.
R3 value, right?
Yes.
Correct. What is there any other dependencies we have?
Okay.
Others, like, is there any? So Salah already mentioned one of the hazards we have, or one of the dependencies. Can you think of others? Come on. So what is this add I? It's reading R3, adding into it 1 and putting the value in R6, which means it needs R3, right? But this add is writing into R3, so it has to wait for this add to finish before doing this add-I, right? Another dependency here. Correct? Is there any other dependency?
And for the last one, we need to overwrite the S3 location after the add operation. So I think.
But is it the case?
This update
is the store updating R3?
No, it's updating a location in a memory.
The memory, right? Because store is a memory operation that writes into the memory. So it reads R3, puts it in the memory location that is computed as this, right?
Yes, but we still need the value of S3 to
exactly, which
memory.
means you need, so you need to read it. That's correct. So it's a read of R3, which needs to wait for for the add to finish the R3 writing first. So another dependency. That's correct.
But Dr. Muhammad, I have a question here. I think it's only one dependency here, like just finishing the first instruction. If I finish it, I will have the data for register 3 for the rest of the instructions. So what I'm trying to say, okay, I did the first instruction, which is the addition. So now I have this value.
What you're saying is correct, but it doesn't mean a single dependency, because a dependency is defined as a relationship between two instructions. And you need to identify this relationship such that, for example, you need to know whether an instruction can execute freely or it has to wait for something else, right? What you are saying here is that the action you are waiting for is a single action, right?
Yes, exactly.
But a single action can stem multiple dependencies. And this is the main purpose of this example, right?
Yeah, but at the end, they will be like all of them are data dependent. I mean, it's not like structure dependent, not control dependent.
All of this, we're talking here about data dependency at all.
Okay.
But there are dependency between that. One last thing that is important to know is that is there any dependency between the load and the add I instruction here? These two instructions, are they dependent in any mean?
Yes.
So can you explain, John, a little bit why yes?
So the reason why I think they're dependent to each other is because you need to read register 3 before you do the instruction add I. And if you haven't read, I guess, this register, you wouldn't know what it is.
Correct. So what you're saying is add I is needing to read R3. But my question to you is that is the load instruction modifying R3? Because if multiple instructions are reading the same location without modification, then reads can happen at any order. It doesn't matter, right? If there is no change. Am I correct?
If there is no change, yes.
Yeah. So my question to you is that is the load changing R3?
Nope.
No, right?
Nope.
That means if you have a read followed by a read to a register, they shouldn't be dependent on each other because the reads can happen at any order. That's okay, right? And that's the main purpose of this question was to highlight this point. So it's an excellent that you got that. So it's basically if you have a read followed by a read, then they are free. There is no dependency at all, right? Good. What else? So let me see. All of them, in fact, are reading R3 here. So the same observation holds for all. Good. Okay. Good. Is there any question you have? Okay, good. Still have some time.
Yes, I have a question.
Yeah, go ahead.
Yeah. So now, if we have only one addition, okay, one addition unit.
Okay.
So I was just thinking about it. Like here, we will use like in the load and the store. I am reading the values in register 3, for example, in the load, and add 8 on it. And this is, and in the same time, or not in the same time, just a minute. No, it will not be in the same time.
For sure, not the same time.
Yeah,
because you stage stuff, right?
Yeah. So not be different. Okay.
Thanks. Okay, we discussed data hazards already, and this is explaining how things happen. Okay, bypassing. That's a good question. So one thing is, how do assume I already have something like this for this dependency. What should I do to solve the situation? The first naive solution is to say, okay, I'm going to wait until I finish the result. So if I write my pipeline diagram, I would say the first add would be fetch, decode, execute, or maybe execute to be X, just to save the terminology, and then memory, and then write back. For the load, I will start the fetch one cycle later. I decode. Once I discover that, oh, I need R3, because when I discover I need R3, you discover this at the decode, because as we explained, the decode stage take the bits from the memory, decode them, which means identify which instruction is that, which operand, and what would be the components to use, like the ALU or the memory, etc. So at the decode, I discover I need R3, but the R3 is only written after the add finishes the write back. So I stall. Stall means just wait. Here, wait as well. And once the write back happens, you can execute and then do the memory and then the write back. Is that clear? So this stalling is what we were talking about earlier, that can cause delays into your CBI. Then here, I also start the fetch. But because we have an in-order pipeline, once you stall everything afterwards, as I was explaining to John, and then you decode, and then you execute. Here, when you execute, the already R3 is written, so that's great. And then memory, and then write back. And then the same thing here, I'm not fetching at all. I start the fetching here. Decode, execute, memory, write back. So if we calculate our CBI for this example, I would say, how many cycles I have taken? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 cycles. I finished 3 instructions. So I take 10 cycles per 3. That's 3.333, whatever. CBI, correct? So it's not 1 anymore, right? Does this make sense? So you increased your CBI a lot because you needed here to wait for or stall for a couple of cycles. But that's bad. But can someone, according to this figure here, propose a solution that can help us increase the CBI and not stall these couple of cycles?
Doctor, why it's a 3? Sorry.
So
over 3.
Oh, we had 4. Sorry, 4 instructions. That's correct.
Yeah,
4.
Okay.
So it's 2.5.
Okay.
Yeah. Sorry. So can someone propose how can we avoid these stalls, or at least mitigate them? If this is our logic, like if this is our data path, how can we handle things?
I have a solution.
Yeah.
So I think we can, like the bypassing, of course. So I think we can let the other instruction, the independent instruction, to go into the pipeline stage while we stall the dependent one.
Oh, but all of them are dependent ones. So what you are saying, okay, what you said is partially correct, but partially wrong. So what you said is bypassing, which will work. But what you are saying is that I would execute instructions out of order. So these are 2 different things, right? Bypassing and out of order are 2 different things. Do you see my point? So bypassing means, it doesn't mean skip an instruction and execute another one. Bypassing means something different. Can someone think of a solution? So let me ask you, like
okay,
a different. Yeah, go ahead.
Are you thinking? Okay, so for example, if we checked all of these instructions, we will see that we will need the address. For example, in store in the last instruction, we will need the value of register 3 to be stored. No, it will not work. Sorry, it will not work.
Okay, so let me ask a question. Good, just to facilitate stuff. and stem some thinking. So this add operation, we assumed is going to be written to the register file.
Okay. Sorry for interrupting.
Yeah, but give me a second moment. Give me a second. So we said that the result would be ready here, correct? Which means it's going to be written to the register file after the write back, which makes sense. But when is the actual addition happened? What is the actual stage where we have the value of R1 plus R2 ready?
After the execution.
After the execution, right? So you did the execution here at the ALU. You got the result handy, so you already have the value. Let's say, for example, R1 plus R2 is 30, right? So here you have 30. Yes, you didn't update R3 yet in the register file, but you already have the result that you're going to write, right? So instead of waiting until you do the write back, you might take the 30 directly and feed it to the input of all the other instructions. Is that clear? Right? This is the concept of bypassing, which is don't wait until the data is ready at the register file. Just pick it directly from the ALU, for example, and feed it to the other fields. And this is the red line here. Previously, everything was waiting, and as you can imagine here, everything being picked up from the register file and fed into the ALU. But now, instead of waiting for this full path, I'm going to pick the result directly out of the ALU and feed it as an input to the ALU. Does this make sense? So the definition of bypassing in architecture is reading a value from an intermediate source. Here is the output of the ALU. And don't wait until it's available from the primary source or the last resort of the data, which is here the register file. Good. Sometimes this is called bypassing because you bypass a stage that you don't need to wait for, or it's called forwarding because you forward the data from a stage, an intermediate stage to another stage. Is there a question?
I have a little bit of a question, I guess.
Yeah.
Could this be considered as the direct memory access or DMA, or is this completely off?
Yeah, okay, that's okay. So DMA is dealing at a completely different granularity. So all of this is happening within the pipeline of the core of the CPU itself. So, but in fact, your question is great because it will help us see the big picture, right? Inside the CPU, we have all of that, right? Then at the higher level, we have CPU or multiple CPUs, and we have a DMA. The purpose of the DMA is to access the main memory directly, get data, and maybe feed it either to a GPU or I/O or something, right? So also DMA is doing bypassing for the CPU caches. This is, I guess, how you connected both concepts. So the concepts are similar, but they are happening at different granularities, right? The CPU bypassing is happening within the pipeline of the CPU itself, and it's bypassing some stages of the pipeline, while the DMA access or the direct memory access goes directly to the main memory, get some data, feed it to the I/O to free the CPU from doing something, right? Does this clarify the concept, John?
Okay, perfect. Yeah, thank you very much.
Thank you so much. And it's a good question that how to put similar thinking in different scales, right? Or different abstraction levels.
Yeah.
So that's good. Okay.
I have also a question.
Go ahead, Salah.
So how long should we keep the temporary results, the bypass data in our pipe?
That's an excellent question. Here, we always bypass after, this is a register, right? You see that this is a register stage, which is after the execution stage, right? Every stage in your pipeline starts with a register and ends up with a register, correct?
Yes.
And by default, once the register is clocked, the data is moved to the next stage and the new data is being written, right? So the data remains for a single cycle. And if you utilize it in a single cycle, that's great. If you don't utilize it, you have to pick it up from somewhere else. Does this make sense?
Yeah, but let's say if the for the same example, the add operation, the SSP it take like more than one cycle to be written in the memory. So,
let's see.
so I think another instruction may be needed.
Sorry, what you mean? Like, let's say this is the example that we're talking about, right? So can you please repeat what you meant?
Yeah, I was saying in this example, we use the bypassing to not stall the load operation, right?
Correct.
The second operation after the add.
Correct.
But let's say the addition itself, it take like more than one cycle after the load to write the data in the memory or the S3 register.
Yeah,
I'm not
in
sure
fact,
this is
here
a
it takes.
register or memory. The S3.
Yeah. This is a register, right? Memory is written like that. This is a register. Yes. So that's a good question, because in fact it takes two stages, because you write at the write back stage while you finish it here. So I guess the answer to your question is to see what happens to this pipeline diagram if we have a bypass, right? So let's see. So previously we had this with no bypassing. Let's see what we have if we have a bypass. Fetch, decode, execute, memory, write back. This is the scenario for the add. And then for the load, I fetch here, I decode here. I need the R3 in the execution to calculate the offset. So I take it from here to here. This is a bypassing.
Okay.
And then you do the memory loading, and then there is no need for write back, but you go through all the stages. And then what about the coming instruction? I fetch the add I here. I decode it here. I know that it needs R3 at the decode. R3 is not ready yet, in fact, right? Because it will be written here. And I need it. Now you will not take it from the execute because you lost it. The cycle passed, right? But in this cycle, the data moved from this register to this register. So you bypass from here to here.
Oh, so we take like from different bypass stage. I mean, we
exactly.
At every
so you
stage
don't have a single
bypass.
bypass. Exactly. This is what was going to be discussed next, which is, in fact, we have shown only a single example of bypass, which is ALU to ALU bypass, which is this one. But in general, you might need bypassing from all stages to all stages. Because here, for example, I need to bypass from the memory to the execute, right? Because this has already a point in the past. The data is not available here anymore. It's going to be overwritten, in fact, right? So if you read here from the ALU, you are going to read the result of the load, not
the load, yeah, S4, right?
Yeah, it's not S4 because S4 is it doesn't use the
sorry,
ALU.
the content of the memory, the 8.
Yeah, it's RL3 plus 8, like the addition that happened in the memory, right? But anyway, you read something that's wrong, right? So you need to read from this register, which this one is holding the actual R3 from the memory. Then what about the last one, which is the store? I do the fetch, decode. When I come to execute to add R7 plus 8, now the write back has already happened. So no bypassing is needed here, right?
Yes.
Because you already finished here and the execute starts here. So it's no bypassing is needed. So in this example, we did two bypassing from ALU to ALU and from memory register to the ALU. Is that clear?
Yes, and who control the operation of selecting the bypass register or stage to?
Yeah, that's an excellent point. So here we have seen only one possible thing, but to be able to tell, even if you have a single bypass, you would still have the option to either read from the bypass or from the actual input of the register file, right? Here. So this is the reason why we put a mux here. So there is a multiplexer, and multiplexer has control bits, selection bits, and those selection bits, answering your question, are being generated by what we call the control unit. That happens at the decode stage. And based on all this logic of the decoding, knowing that which register you need, what are the current status of different registers, it generates the correct selection bits to tell the ALU or the execution unit in general which path to select. Do I want to select this path, which is the normal one, or do I need to do the bypassing? And should I get the bypassing from here or from here? So because you have multiple bypasses as well, right? Here again, we read from the ALU, but also you read from the memory, which is the other one that we have done, right? So this is controlled by the selection logic, which is generated by the decode stage. Good?
I see. I see. Thank you.
Thanks. Is there any question? Okay. Okay. Yeah, this is what we were saying, that the bypass logic.
I have a question.
Go ahead.
I was just thinking about it. Like the control signal, we said that it will be generated from the decode stage. But is it the decode stage only or the decode stage with the fetch stage? Because like
the only purpose of the fetch is to bring the memory location of the instruction, the actual thing, into the register, right? But then decoding the instruction, understanding the situation, what are your operands, which ones you need to write to, which ones you need to read to, checking the dependencies, all of this is done by the control unit at the decode stage.
Yeah, I see. So we will keep an old version of the previous instruction then?
You keep track of all what is going on in the pipeline right now, right?
Okay,
so the control unit, what is shown here is called the data bath, right? Which is what is happening for data across different stages. But there is also the control bath, which is a combinational logic that generates all the logic that controls these signals, right?
Yeah, I see.
Yeah. Okay, good. When I was teaching this course to undergrads, what we used to do is to have a project that they build this processor in RTL such that they are able to calculate the combinational logic. They see how it works in pipelining, so they have a feeling of that, right? But at least hopefully you guys get the concepts. Okay, so we still have some time, which is good. I guess we already explained this by passing here. That's good. Have we prevented all data hazards? Okay, stalls can prevent some, but not all, and that's good. So let's take this example. Assume I have a load instruction, so I would just write them in order. So I would say I have a load instruction that is writing to R3, 8, R2, and then it's followed by an add that does this, R4, R2, R3. First of all, let's identify what is the dependency here. Load is going to the memory, reading some data, and then writing into the register. So what is going to happen for the load is go to the memory with R2 plus 8 address, read the data in this address, place it in R3. So load is going to update R3, correct? And then the add needs R3 as an input. Good? Can someone imagine what is the problem with that? The problem is the load will not finish, will not have the value of R3 after the execute, similar to what we assumed before. When does the load operation happens? The actual load operation from the memory, at which stage? If I write the pipeline block here of the load, like fetch, decode, execute, memory, write back.
At the write back?
No. Write back will update the register, yes, but when is the actual even load happens, right? Because everything happens at the write back by updating the register file. But previously in the add, we said the actual value of the addition is ready here, right? So my question is when the actual value of the data that brought to the memory will be ready?
In memory.
Yeah, at the end of the memory stage, right? Because the memory stage main purpose is to go to the cache or whatever and bring the data, right? And then in the write back, update the register for that. So the data will be ready here. On the other hand, if I'm doing my add, I will do fetch, decode. I come to execute, but I need R3. But I cannot bypass like what I have done before because it's not ready here. I need to wait here. So you have no option other than stalling for one cycle and then execute. Do the bypass from the memory and then execute. Does this make sense? So in this case, even with the bypassing we have done, you still under certain scenarios will pay the cost of stalling for a single cycle. If we didn't have a bypass at all, how many cycles we would have to stall for?
This will be 3, I think. 2 from the first one, and 1 from like 2 waiting. The load will wait 2 stalls to have R3 from the first instruction, right?
But the load is the first instruction, right?
Oh, the load is the first instruction, so it will be just 2 stalls.
True, right? I'm stalling here. When R3 will be ready, it's after the write back, right? As usual. So if I don't have any bypassing logic, I will wait until the register file is being updated by the write back, stall here, and then do the execute and continue. But because we had a bypass logic, which can read from the memory directly into the execute, I saved 1 cycle, but you still suffer from the stall of a single cycle. This makes sense? Yeah, so this is here what's mentioned. The hardware solution detect this situation and they inject the stall cycle. Another solution which will be the reordering stuff. So if I find such situation, I will try to insert some instructions in between them to make sure that they are separated such that the add gets shifted without stalling. But this is an out of order execution that is not allowed in order pipelines. Will only come when we have out of order execution. Good? Okay. This is usually has a term in architecture called load to use dependency, because load to use dependency will enforce you to not just have a bypass logic but also have a stall logic, right? Okay, good. Now maybe taking some example of performance calculations. How to calculate the performance impact or delay due to the load use. Load use means what? Means you have a load instruction that is bringing data that is coming instruction is going to use, right? So if I have the same things that I had before, like you have a load 20%, store 10%, other operations like arithmetic 50%, branch 20%. And then I'm telling you that 50% of the loads would be followed by a dependent instruction, similar to the scenario we had here, right? This one. So how to calculate the effective CPI? Originally, I would have a 1 CPI, right? This is the ideal CPI without any stalls. But now, this situation would require some stall, as we mentioned. So this is require one cycle stall, correct? How to calculate this effect? I would say I have 20% load operations. 50% of them are causing me an additional 1 cycle. Then I add all of this effect into the 1 cycle ideal CPI. This increases my CPI to 1.1, which means this causes me a 10% lose in the performance. Does this make sense? Is there a question? Taking this into practical scenarios, most of the current processors, in addition to being out of order, in fact, they also employ special prioritization for load operations. For example, if you go to the off-chip memory like the DRAM, you will find that the DRAM doesn't only do first ready, first come, first serve scheduling. In fact, if they have reads and writes, they prioritize reads over writes. Why? The answer is in this slide, which is loads can cause pipeline stalls, while writes will not, right? So having higher priority for loads will prevent such situation because they will make the load accelerated. Instead of waiting for a single cycle, you might need to wait for more if you go for the off-chip memory and you don't prioritize reads. Is there a question? Okay. Yeah, this is causing something like out of order execution. Let's say, for example, here, I have a load dependency because load is writing into R4 while the add-I is reading that, and we have to stall for 1 cycle. But leveraging the fact that this instruction is not dependent on the load, I might be able to bring it in between the load and the add-I. So I do reordering, bring the sub here, and now we don't need to stall for any cycle because, I mean, naturally the add-I execution will come after the memory operation is ready by just delaying it with a single instruction. Again, this is not possible because this is out of order execution, so it's not possible for in-order pipelines. But usually this is what happens in reality. Even the compiler itself will be doing this reordering for you. Are we good? Or are you guys lost? Okay. Good. So now another question or another investigation of what might be other dependencies would happen. We discussed arithmetic dependencies like add to load, add to store. Unload use stall, which is a load followed by an instruction that is dependent of the load. Now what about load to store? Let's say I have something like this. I have a store instruction that is writing to R5, and then this is a memory operation that is 8 plus R1. And then this is followed by a load where I am reading, sorry, I'm writing R4 by getting the data from the memory at the location 8 R1. What do you think? Is there any dependency here? Guys, come on. Like, what do you think? Just think loudly, right? It's okay to be wrong, right? We're just trying to increase our way of thinking in our architecture terminology, right? So let's think together, see what's happening, why this is wrong, why this is not wrong. I don't want just to give you the answer directly, right? Hello?
I think it may depend on two things, for example. So what I'm trying to say, like now I will get my address for the store and load. Like the data is in R5 and R4, correct?
The data is in R5. What do you mean by the data is R5 and R4?
Now I will store data. I will store the data from register 5 to location of the memory, which is the address.
Correct. You're doing this. And
yeah, and then I will do, yes. So just like I will need to get the address, right? So both of them are mapping to the same address at the end. The first one, I will need to store the data into the memory. And the second one, I will need to load the data from this location of the address from the memory into the register 4. So there is like a dependencies here, and we will need to stall, I think, to make sure that I will write back the data. I will write the data into the memory from the first instruction before I load it correctly to the other register.
Okay. What others think?
Thanks,
Mohammed, for that. Yeah, go ahead. Sorry, go ahead.
Yeah, there was another thinking.
Yeah, go ahead.
If it's good or not. Like, okay, I'm seeing here like the storing and loading, they are doing, they are related to the same address. So I will generally like, if the controller is smart enough, it will move the data from R5 to R4 directly. I'm not sure if it can be happen or not, but I would think.
Okay, that's also good thinking. Yeah.
Yeah. So
are there other ideas?
For me, no.
Yeah, thanks, Mohammed. Thanks. Yeah. Sorry, I was asking others, but yeah, thanks for the couple of additions. Both are great, in fact. What others think? What do you think? So first of all, R1 is being read or being written by both instructions?
It's read.
Read. Great. And we said before that read and read, there is no problem at all in dependency, right? So if I write the pipeline diagram, I do fetch, decode, execute the LEU operation itself. So I'm reading R1 here, perfect. For the store, I'm doing the store in this memory operation and then doing write back. If I do the load to see if there is a hazard or not, I just write the pipeline diagram again, fetch, decode. For the execute, I'm reading R1, no problem, because this store is not writing to R1 anyway. And then for the memory operation here, what I'm doing, I need to read the memory and write it to R4, right? So which will happen at this stage, which anyway, after the store had finished, there is no hazard, and then I'm done, right? So between the R1 and R1, in fact, there is no dependency at all, right? This makes sense? There might be some structural dependency because you need to write and read from the same memory location, but hopefully this is not happening on the same cycle and you are good, right? So ultimately, if you get confused, just draw the pipeline diagram and think of what happens at each stage. Here, the store is happening here, perfect. Now I'm loading from the memory here, so the store should be done already. And I'm just reading the value from the memory into the R4. And that's it. So there is no dependency at all in this case, right? Or in other words, there is no dependency problem in this case. Is that clear? Okay.
But if we do reordering, it will be a problem, right?
Well, that depends on, so I guess your question, Salah, is maybe you cannot move the load before the store, right?
Yes.
Generally, yes, you are correct, right? Yeah, because of consistency issues, but this is a problem that we will discuss later. Yeah, thanks. Okay, so we said, so all what we discussed right now is data hazards. Now let's look into structural hazards. So structure hazard is you have two instructions that try to use the same hardware, the same resource on the same time.